All right, here we go. Number 13. In problem 4. So that is this guy right here, the roller coaster problem, okay? We start at a height of 42 meters. The mass of the roller coaster is 25 kilograms. And we're going to go along the ride. And they're asking us questions here. What is the speed of the car at point A, B, and C? And how high will it go up this ramp right here? Okay? I forgot to mention, the speed of the roller coaster at this spot is 17 meters per second. So before we answer the questions, let's just conceptually talk about what's happening here. I've got kinetic energy and I've got potential energy, so I'm going to have a K plus U at that spot, right? And as it moves through the roller coaster, because we're neglecting friction, it's a frictionless roller coaster in Fantasyland, okay? We're going to increase our speed, decrease our speed, and all the while, the K and the U amounts will change, but their sum will stay the same. So that means when I get to point A, because it's the same height, I have the same amount of U, so I'm going to have the same amount of K. So that means for part A, the velocity at point A will be the same as it was at the beginning, and that's 17 meters per second. Okay? Then at spot B, now my height is half. So first let me show you the solution where I just appeal to your common sense and what seems like the logical in the problem. And certainly there's nothing wrong with this, but then I'm going to show you my preferred way. But I know many people would do it this way, so I'm going to show you this way first. Well, if the height is half, because the equation for M is mgh for potential energy, if the height is half, the PE is half. And when I use delta H of 21, which is half of 42, I get the amount of potential energy associated with this change in height. So that means whatever kinetic energy I had at the top, now when I get to point B, my new kinetic energy is going to be the old kinetic energy plus the change in the potential energy. And so plugging in my numbers for 1/2 mv squared, there it is. And then my change in PE, that number right there, add those up. This is my new amount of kinetic energy at location B. And of course, kinetic energy is equal to 1/2 mv squared. So I solve that for V, and I see that that's how fast it is going at point B. Faster than 17, of course, because when it's higher, it's going to be going slower, and when it's lower, it's going to be going faster. And that's what we saw. Now, for part location C, now I'm at the very lowest point. And this is why I was saying if you choose your lowest point to have a height of 0, then when you set up your equation, then you don't have a potential energy term at all to deal with. It will become 0, and it simplifies your equation. So at the beginning, I was going at 17 meters per second, and I was at a height of 42 meters. Now I'm at the bottom. That mgh term completely goes away. Of course, just as always, the m's are in every term, so they cancel out. And now I can solve this for V final. And at a lower point still, right? At point B, I was going 26.5. Now I'm at the very bottom. I'm going even faster. This, of course, is the fastest the roller coaster will be able to go. Unless it goes below ground level, this is the fastest the roller coaster will go. And then part D asks, how high will it go up this slope here? And of course, that's where it runs out of speed. So at the very highest point, the velocity is 0. And how high is it? This is what I'm going to solve for right here, this h. So solving for h, there's the algebraic solution. Plug in the numbers, and there you see, that's the highest it will go. 56.7 meters is where all the energy now will be in the form of potential, and it will have no velocity. Of course, it will want to roll backwards unless something prevents it from rolling backwards. That's what's going to happen. But that's as high as it's going to go. I said up here that I was going to appeal to your common sense, But I want to show you this is my preferred method. So going back to part B, if I had done part B this way, which says the total amount of energy doesn't change, it's the same at the beginning as it is at the end, and the beginning and the end can be any 2 points you choose. Okay, any 2 points along the trip of the roller coaster. So M's cancel out, and when I solve this for VF, which is what I want to find, right? This was part B. How fast is it going at a height of 21 meters? So I can solve this for VF. And of course, I get the same answer as I did when I did it this way. But I just wanted to emphasize, I prefer, and I think it's a good idea, to start off your conservation of energy problems with this equation right here. And then I think the last part of the question asks how, let's see, if we substitute a second car with twice the mass, what then are the answers to A through D? Well, if you look, this is what happens. The M's cancel, so the mass doesn't matter. So no change to your answers. They'll all be the same. And if you're going to ride on the roller coaster, this is a good thing, because what if you got on the roller coaster with a lot of big people? Or you got on the roller coaster with a lot of small people? Or you got on the roller coaster all by yourself? You want the roller coaster to behave the same no matter how many people are in it and no matter what the mass of the car is. So that's a good thing, actually.